So in the today's class, we will study uh, on the work. So how work is defined mechanically and thermodynamically. We will see here. If the energy crossing the boundary of a closed system, it is not heat, then definitely it must be a work. So how we will define this mechanical definition of work? So work is the energy transfer associated with a force acting through a distance. So when we keep one object from one place to another place by applying a force, then we are going to call it as a work. So it is the energy transfer associated with a force which is acting through a distance. So how we will represent it W? W indicates work. Work is equals to integration of 1:2, means from one point to second point. It is F into dx. When we apply a force, it is acting through a distance. So work we are going to represent mechanically like this way. So in thermodynamics, we define work with the concept of system, properties and the processes. So work is done by a system if the sole effect external to the system could be the rising of a weight, rotating shaft, a rising piston, electric wire crossing the boundary of a system are all associated with the work transfer. So now let us see, with the help of a sketch, a thermodynamic definition of work. So you can see here, let us consider a battery. This battery is running the motor, and this motor, it is driving a fan. So here now let us consider this battery and the motor as one system, and this is the boundary. This is nothing but the imaginary boundary, and this is my surroundings. You can see here, now this motor is driving the fan. Here the system is doing the work on the surroundings. To understand the concept of the thermodynamic work, now let us replace this fan by this pulley and the weight as shown in the figure. So this fan is replaced by this pulley and the weight which is shown in the figure here. So as the motor rotates, this pulley also rotates. Here the weight may be raised with the pulley which is driven by the motor. Hence the sole effect of the energy transfer to the things external to the system. So here also we have considered it as a system only. Here the sole effect of energy transfer external to the system could be the rising of a weight. So as the pulley rotates, this weight is going to be raised or lifted up. So here we can tell that the work is done. The work is done here. Now let us see some formal sign conventions for heat and work interactions. So if this is the system, if the work is done by the system, then we are calling the work as positive. W is positive here. If the work is done on the system, then we are considering this work as negative. You can see here heat transfer to a system. Heat is transferring to a system, and the work done by the system are considered as positive quantities. Whereas heat transfer by a system and the work done on a system are considered as negative. So you have to remember these things. So these are very, very important while solving the problems. So when the work is done by the system, work is considered as positive quantity. And the work is done on the system, then W is considered as negative. Suppose heat is entering the system or heat is transferred to a system, then we are considering that heat transfer as positive quantity. When heat is transferring from a system or heat is leaving a system, heat is transferred by a system, we are considering it as negative here. So similarly, how we have written for heat transfer, so here also we'll write for the work done. The work done during a process between states 1 and 2 is denoted by W12 or simply W. Here also the work done per unit mass of a system, it is denoted by small w, that is work done per unit mass. It is denoted, it is having the units kilojoules per kg. And the work done per unit time, it is called as the power. So how much work is done means the rate of work. Rate of work is nothing but power only it is. The work done per unit time, it is called power and it is denoted by W dot. So already we have explained it. Over dot, it stands for per unit time. The unit of work is kilojoules per unit time, or it is kilowatt. Now let us study what are the similarities between the heat and the work. You can see here both heat and work are the boundary phenomenon because both are crossing the boundaries of a system. So already the sketches already we have shown it here how heat and work are crossing the boundary of the system. For that purpose both heat and work are boundary phenomenon. Next, here both heat and work are path functions. That means it depends on the path followed during the process as well as the end states. Here both heat and work are path functions. They depends on the path followed, but they are independent of the states. We will prove it here in the next class how heat and work are called as the path functions. We will prove it. Both are associated. Both means both heat and work are associated with the process, not a state, because it is depending on the path. So when the path takes place, then definitely we are calling it as a process. It is not depending on the end states. It is not a state. So unlike properties, heat and work has no meaning at a state. That means initial state and final state. It is not having any meaning because these are dependent on the path followed during the process. So these are the some similarities between heat and work.